Hi everyone, so today we are going to be using sort of a Khan Academy style video, and I'm going to illustrate for you what covalent bonding is all about, specifically nonpolar covalent bonding and how that contributes to the pole moment of a particular molecule. So that's whether it's polar or not polar and which end is which. So let's get started. So we'll start out by making our topic up here at the top. So oh no, what's happening? I picked that. I picked that. Okay, I think I got it. Okay, so let's start there. Nonpolar covalent bonds, right. So I'm going to use the example of water, and that's just because it's easiest to demonstrate this with the familiar molecule, so I picked water for that reason. So I'm going to go get a different color real quick and use some water using that color. Okay, so I'm going to start with the nucleus of water, and I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8 protons. So I'm going to denote that they're protons by putting a little plus in each of them. And I'm going to actually leave the neutrons out just for clarity's sake. So you should assume that they're there. Just I'm not going to waste time drawing them because this whole relationship is really all about protons and electrons rather than being about neutrons. So I'm just going to leave them off. I'm going to pick a different color for my electrons, and remember that electrons come in shells. So first thing I'm going to do is draw my shells. So I know that oxygen has 2 electron shells, and now we need to populate those shells with some electrons. So, oopsie, I already made a mistake. So remember, we can't actually fill the shells the way I just did. We have to do it differently, and that's because of the way that the rules of electron shell filling works. So I actually have to fill in this innermost one in first. And so the innermost shell holds a maximum of 2 electrons, and the outermost shell holds a maximum of 8, but I've already used up 2. And we know that in neutral species of atoms, the electrons and the protons are going to equal each other in number. So if I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, okay, 8 protons in there, I should have 6 electrons left to use to fill this one because I've already used 2 up. And remember also electrons like to be in pairs when possible, so here's a pair, here's a pair, and here are 2 singletons. And remember, the reason that these 2 don't pair up is because they probably have the same spin. So now I have an oxygen atom that is ready to bind with something else. Another thing I'm going to do real quick here is write a little minus in each one of these so we know that they're electrons. All right, so let's go back and we're going to draw our hydrogen nucleus nearby. So 1 proton and 1 proton. And remember, hydrogen doesn't have any neutrons anyway, so I don't have to worry about those. So now what I'm going to do is come over and draw my electron shell. And let's give ourselves a little electron here. And I'm going to put a little minus in there just to remind myself that it's negatively charged. There we go. Okay. All right. So we're going to make a polar covalent bond. And we're going to do that by allowing these two pairs. Oops, that's not quite dark enough. There we go. These two pairs of electrons are going to be shared. So they're going to be shared between the oxygen and the two hydrogens. And that's going to give us our covalent bond. So the kind of key for covalent bonding to remember how it works is to think share a pair. And that's because a single covalent bond represents the sharing of one pair of electrons rather than a single one. So I'm going to redraw parts of this such that the pair is shared. So bear with me for a moment while I do that. All right, so let's repair this a little bit. And there's our electron shell. Now I'm going to pick a different color to do some electron drawing. So there's our two shared pairs, but of course we can't forget that we need to include some protons. And of course, for each hydrogen, there is only one. Okay, so now I've created my two covalent bonds. So if I was going to draw a simplified structural formula for this, water is a molecule that looks like this. So the bond angle is about 90 degrees. Now, I want to show you non-polar covalent bonds specifically, and I haven't really addressed that yet. So let's first talk about the concept of electronegativity. So electronegativity is defined as an atom's ability to attract, not attract, I was thinking about the word attack, attract and hold onto electrons. So in lecture, if you want to go review for lecture, I gave you some math about what you can expect depending on the electronegativity. So more than 2, between 0.5 and 2, and less than 0.5. So electronegativity differences are what determine whether a bond is polar or nonpolar. So if you have electronegativity A minus electronegativity B, and you find that the electronegativity difference is less than 0.5, then that's going to be, for example, a nonpolar covalent bond. So that's the math end of it, and you can go review that in the Chapter 2A lecture if you want, but for this particular video, I'm trying to show you a simpler way to think about it. So I'm going to erase all this, and we're going to make a little illustration down here. Okay, so what I'm going to do is draw myself a rope. So here's my rope. And we're going to play tug-of-war. And we're going to think of protons as being the units of force available to pull on electrons with. So the rope is representing electrons in a shared pair, and the protons are representing team members. So this over here is team oxygen. And over here we have team hydrogen. So if we think of protons as units of force available to pull on electrons with, oxygen is going to have 1, 2, 3, 4, 5, 6, 7, 8 strong pullers on its team. And hydrogen over here within one of these bonds only has 1. So, look at this picture for a minute and imagine it's a tug-of-war. Which team do you think will win? If you said oxygen, you are of course correct, because oxygen has 8 times as much pulling power as hydrogen. So these are still being shared, they're just being shared unevenly. So what that means for an electron perspective is, keep in mind, if I were to draw the trajectory of an individual electron around the nucleus of an atom, so let's draw that imaginarily. I'll first draw you what it doesn't look like. It doesn't look like this. Oops. Well, that's fine. I'll just keep black. Let's actually change to green. So what it doesn't look like is, it doesn't look like this. So note that this looks a lot like Saturn, where the electron is rotating, but only around sort of the equator of the nucleus. That's not really how atoms rotate. They don't stick to one plane. They have multi-planar rotation at their disposal. So what that looks more like, although it's less easy to illustrate, is the following, where you have electrons whizzing around this way, and then maybe they change this way, and they go this way. So they can change the plane of rotation a lot. And if you were to sort of spin this out conceptually into a lot of different rotations, what you sort of end up with is a cloud. Because the electrons are spinning so fast that what you end up with is a cloud of probability where you might find the electron if you could manage to stop it, but you can't. So when we say electron shells, what we really mean is this cloud at a fixed distance from the nucleus. So if the electron is whizzing around the nucleus, but it's also being shared with another nucleus, let's draw that out. So I'm going to simplify this bond right here way down, and I'm going to look at one electron splitting its time between this cluster of 8 protons and this cluster of 1. So first let me set up my proton groups. So over here we have the one proton nucleus. So that's the nucleus that belongs to hydrogen. And over here we have the 8 proton nucleus. That's the one that belongs to oxygen. And then I'm going to use this green color to trace the path of an individual electron as it makes its orbits around each of the respective nuclei. So watch what I do here. Okay, I'm done rotating. So what you can see is the electron does spend some time over here. But it spends way more time over here. And that's because, remember, there is 8 protons over here attracting that electron, versus over here there's only 1. So within each of these shared pairs over here, this electron is going to be doing that, and so is this one. Which means that the total number of electrons circling oxygen's nucleus, because it has its valence needs met, is 8. The total number of electrons circling each hydrogen nucleus is also 8, but the amount of time that these electrons spend near the oxygen nucleus is more. So let's erase that and draw it in the form of electron clouds. So all right, and I'm going back to my paintbrush, and let's get a different color. So the green color represents the electron cloud, so the cloud of probability where you can find an electron, so it's negative charge. So the negative charge on this side, so here's the nucleus, so that needs to be darker. So this end of the particular molecule is going to have a slightly negative charge because there's more greenness over there, and this end will have a slightly positive charge because there's less green there. So this kind of pinball or figure 8, not pinball, excuse me, bowling pin or figure 8 configuration of an electron cloud represents a nonpolar covalent bond. So nonpolar, covalent. So these two clouds aren't separate as they would be in an ionic bond, but they're definitely not the same size. Nonpolar covalent bond. And this one happens to be shaped like this. Okay, so hopefully that clears up the relationship between protons and electrons and how they behave when they're shared, and specifically the way that they're shared when there is different electronegativity across the two atoms sharing the electrons. And as always, if you have questions about that, or if it still isn't clear, absolutely come talk to me in office hours or in class, and I'll be happy to try and explain it a different way. But in the meantime, thank you so much for your attention, and I hope you enjoyed this video.